There is a boundary in the universe that you can cross but never uncross, a threshold that looks like nothing, feels like nothing, and announces itself with nothing. No wall, no flash, no sound, no sensation of any kind. And yet, the moment you cross it, you are gone. Not dead, not destroyed, gone. Separated from the rest of the universe by a barrier more absolute than any wall, more permanent than any prison, more silent than any grave. That boundary is called the event horizon, and what lies beyond it is one of the most disturbing questions in all of science. The event horizon is not a physical thing. It is not made of matter, or energy, or force. It is a mathematical boundary, a surface in space-time defined by a single, terrifying property. Once you cross it, no path, no trajectory, no speed, not even the speed of light, can carry you back. The geometry of space-time itself has folded in on you. Every direction you could move, including the direction you came from, now leads deeper inside. The future itself has bent inward. And your future, every possible version of it, ends at the same place, the center of the black hole, where the laws of physics themselves break down. Something is wrong with our understanding of what lies beyond this boundary. Something deep and fundamental about the way we think about space, time, and the nature of reality must be revised. The singularity is the proof. The information paradox is the proof. The firewall is the proof. Every paradox and every contradiction that arises at the event horizon is evidence that our current theories are incomplete, that a deeper theory is needed, and that the resolution of these paradoxes will transform our understanding of the universe. Right now, at this moment, there is an event horizon at the center of our galaxy. It belongs to Sagittarius A star, a supermassive black hole with a mass of roughly 4 million times that of our Sunday. Its event horizon has a radius of approximately 7.5 million miles, roughly 17 times the distance from the Earth to the Moon. If you could stand at the edge of this horizon, you would see the universe above you, compressed and blue-shifted, the stars crowding together in a shrinking circle of light, and below you, darkness. Not the darkness of empty space, but the darkness of a future from which nothing returns. The event horizon of M87 star, the supermassive black hole at the center of the galaxy Messier 87, is even larger. Its mass is roughly 6.5 billion solar masses. Its event horizon diameter is roughly 24 billion miles, larger than the orbit of Pluto. It was the first black hole ever photographed by the Event Horizon Telescope in 2019. Its shadow, a dark absence of light, ringed by a glowing crescent of superheated gas. Consider the scale of the mystery. The event horizon of Sagittarius A star has a circumference of roughly 47 million miles. Light would take about 4 minutes to circle it. The event horizon of M87 star has a circumference of roughly 76 billion miles. Light would take about 4.5 days to circle it. Behind each of these horizons lies a region of space-time that no observation can ever reveal. The event horizon is the most absolute barrier in nature, more permanent than any wall, more impenetrable than any shield. And behind it lies the deepest mystery in physics. The event horizon is also deeply personal. It is a boundary that a human being could cross, at least for a supermassive black hole, without feeling anything unusual. You would not know the moment of crossing. No alarm would sound. No sensation would mark the transition. You would simply be inside, separated from the rest of the universe by a boundary you never noticed crossing. And then, every possible future would lead to the same destination, the center, where physics itself breaks down. The most absolute prison in the cosmos has the gentlest entrance. Every large galaxy we have ever observed harbors a supermassive black hole at its center. The Milky Way alone may contain hundreds of millions of stellar mass black holes. The observable universe, with its 100 billion galaxies, is saturated with event horizons. And behind every event horizon lies a region of space-time that we cannot observe, cannot probe, cannot access. A region whose properties we can only infer from theory. A region where our two greatest theories of nature, general relativity and quantum mechanics violently contradict each other. By the end of tonight, you are going to understand what lies beyond the event horizon, what general relativity predicts, what quantum mechanics demands, and why the two cannot agree. You are going to follow the journey from the moment of crossing to the approach to the singularity. You are going to learn why space and time switch roles inside a black hole, why the singularity is a moment in the future rather than a place in space, and why the information paradox, the firewall, and the holographic principle have transformed our understanding of what the event horizon really is. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. What lies beyond the event horizon is not just an unanswered question. It is a question that, when answered, will reveal the deepest truths about the nature of space, time, information, and reality itself. The event horizon is not just a boundary around a black hole. It is the boundary of human knowledge, the frontier where the known universe ends and the unknown begins. And crossing it, even in theory, even in mathematics, even in imagination, is the most profound journey that physics can contemplate. The event horizon is also the most studied boundary in theoretical physics. More papers have been written about it than about any other single object in the cosmos. The reason is simple. The event horizon is the place where general relativity and quantum mechanics collide most violently. It is the stress test for every theory of quantum gravity. Any candidate theory must explain what happens at the horizon, what lies beyond it, and whether the classical picture of a smooth crossing is correct, or whether quantum effects modify it in some dramatic way. The event horizon is not just a feature of black holes. It is the benchmark against which every theory of fundamental physics must be measured. The questions it poses about information, entropy, unitarity, and the nature of spacetime are the deepest questions physics has to offer. Now, let us begin. To understand what lies beyond the event horizon, we must first understand the event horizon itself, what it is, how it forms, what it does, and why crossing it is so fundamentally different from crossing any other boundary in the universe. The event horizon is a prediction of general relativity, Albert Einstein's theory of gravity, published in 1915. In general relativity, gravity is not a force. It is the curvature of spacetime caused by the presence of mass and energy. Massive objects curve the fabric of space and time around them, and other objects follow the straightest possible paths through that curved geometry. These paths are called geodesics. The Earth orbits the Sun not because the Sun pulls on it with a force, but because the Sun curves space-time around it, and the Earth follows the natural contours of that curvature. The equations that encode this physics are Einstein's field equations, 10-coupled, non-linear partial differential equations that relate the geometry of space-time to the distribution of mass and energy. Solving these equations exactly is extraordinarily difficult. But in 1916, within months of Einstein's publication, the German physicist Karl Schwarzschild found the first exact solution, describing the spacetime around a perfectly spherical, non-rotating, uncharged mass. Schwarzschild was serving on the Eastern Front of the First World War and suffering from a fatal autoimmune disease when he derived his solution. He sent it to Einstein, who presented it to the Prussian Academy of Sciences in January of 1916. Schwarzschild died in May of that year, never knowing the full significance of what he had found. The Schwarzschild solution revealed a remarkable feature. At a particular radius, now called the Schwarzschild radius, the spacetime geometry undergoes a dramatic change. If all the mass of the object is compressed within this radius, a boundary forms, a surface in spacetime from which no signal, not even light, can escape. This boundary is the event horizon. The Schwarzschild radius depends only on the mass. For our Sun, it is approximately 1.86 miles. To form a black hole from the Sun, you would need to compress its entire mass, all 2,000 billion kilograms, into a sphere less than 4 miles across. For the Earth, the Schwarzschild radius is approximately 9 millimeters, less than a centimeter. For a human being of 70 kilograms, It is roughly 10 to the power of negative 25 meters, far smaller than a proton. These numbers reveal that ordinary objects are nowhere near compact enough to form event horizons. The Sun's actual radius is roughly 432,000 miles, more than 200,000 times its Schwarzschild radius. To create an event horizon requires compressing matter to extraordinary densities that nature achieves only through the death of massive stars. When a star more than roughly 20 to 25 times the mass of our Sun exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses. The outer layers are expelled in a supernova explosion, one of the most violent events in the cosmos, capable of outshining an entire galaxy for weeks. The energy released is roughly 10 to the power of 46 joules. The elements scattered by the supernova, iron, gold, uranium, carbon, oxygen, are the raw materials from which planets and life are assembled. If the remaining core exceeds roughly 3 solar masses, no known force can halt the collapse. The matter contracts past its Schwarzschild radius. The event horizon forms, and the matter continues to fall inward toward the singularity at the center. This entire process, from the exhaustion of fuel to the formation of the event horizon, takes less than a second. One heartbeat, and a star becomes a black hole. The formation of stellar mass black holes through supernova explosions is not the only mechanism by which event horizons can form. Supermassive black holes, those with masses of millions to billions of solar masses, are found at the centers of nearly every large galaxy. Their formation mechanism is less well understood. They may have formed from the direct collapse of massive gas clouds in the early universe. They may have grown from smaller seed black holes through accretion of matter and mergers with other black holes. They may have formed through some combination of these processes. What is clear is that they are common, that they are massive, and that each one has an event horizon behind which lies the unknown. The relationship between a galaxy and its central supermassive black hole is not coincidental. Observations have revealed tight correlations between the mass of the central black hole and properties of the host galaxy, such as the velocity dispersion of stars in the galactic bulge. This correlation, known as the M-sigma relation, suggests that the growth of the black hole and the growth of the galaxy are intimately linked. The black hole shapes the galaxy through feedback processes, heating and expelling gas through powerful jets and radiation, regulating star formation across the entire galaxy. A single object, hidden behind an event horizon, controls the fate of hundreds of billions of stars. Active galactic nuclei, the most luminous, steady sources in the universe, are powered by matter falling towards supermassive black holes. As matter spirals inward through an accretion disk, friction heats it to millions or billions of degrees. The innermost regions glow in X-rays. The disk can outshine the entire host galaxy by factors of hundreds. The energy source is gravitational potential energy, converted to radiation with an efficiency that dwarfs nuclear fusion. Up to roughly 40% of the rest mass energy of the infalling matter can be radiated, compared to less than 1% for nuclear fusion. The most efficient energy source in the universe operates just outside the event horizon. The Blandford-Znaiec process, described in 1977, shows how magnetic fields threading the ergosphere of a rotating black hole can extract rotational energy and launch powerful jets of matter and radiation from the poles. These jets extend for hundreds of thousands of light-years, far beyond the host galaxy, shaping the intergalactic medium on scales of millions of light-years. The energy that powers these jets comes from the rotation of the black hole, tapped through the magnetic fields of the accretion disk. The event horizon sits at the center of this cosmic engine, the boundary beyond which the energy cannot be recovered. In 1939, J. Robert Oppenheimer and Hartland Snyder published the first mathematical demonstration that this process is inevitable for sufficiently massive stars. Their paper showed that general relativity predicts the formation of event horizons as a necessary consequence of gravitational collapse. Gravity always wins. The term black hole was popularized by John Archibald Wheeler in 1967. Roger Penrose proved in 1965 that singularities are unavoidable behind event horizons. Stephen Hawking extended this work. Together, The Penrose-Hawking singularity theorems established that event horizons are not rare or exotic. They are common, generic, and inevitable features of the universe described by general relativity. The concept of the event horizon was initially met with deep skepticism. For decades after Schwarzschild's discovery, most physicists believed that the peculiar behavior of the metric at the Schwarzschild radius was a mathematical artifact, a consequence of the choice of coordinates, rather than a physical reality. It was not until David Finkelstein published a paper in 1958 that the true nature of the event horizon was clarified. Finkelstein showed that by choosing different coordinates, the singularity at the Schwarzschild radius disappears, revealing the horizon as a smooth, well-behaved surface that can be crossed without drama. The apparent singularity was a coordinate artifact. The real singularity, at the center, was not. This distinction between the coordinate singularity at the horizon and the true singularity at the center is crucial. The horizon is not a place where physics breaks down. It is a place where certain coordinate systems break down, much as the coordinates of latitude and longitude break down at the North Pole. The horizon is physically smooth, the center is physically singular. The two are separated by a region of spacetime whose properties are the subject of this entire inquiry. The Chandrasekhar limit, established in the 1930s, showed that white dwarfs above roughly 1.4 solar masses must collapse further. The Oppenheimer-Volkoff limit, established shortly after, showed that neutron stars above roughly 3 solar masses must collapse past their event horizons. These mass limits are among the most important results in astrophysics because they establish that event horizons are not hypothetical. They are inevitable outcomes of the deaths of sufficiently massive stars. The number of stellar mass black holes in our galaxy is estimated at hundreds of millions. The number in the observable universe is beyond meaningful count. Each one has an event horizon. Each one has an interior that we cannot observe. The universe is filled with blind spots, regions of spacetime forever hidden from view, containing physics that we can only infer from theory. The event horizon is the most common boundary between the known and the unknown in all of nature. The Schwarzschild radius provides a useful lens for understanding the range of event horizons in the universe. For the Earth, the Schwarzschild radius is roughly 9 millimeters. For a human being, it is far smaller than a proton. For the Sun, it is roughly 1.86 miles. For a neutron star of 1.5 solar masses, the physical radius is about 12 miles, while the Schwarzschild radius is about 2.8 miles, meaning neutron stars are not far from being black holes themselves. For a stellar mass black hole of 10 solar masses, the Schwarzschild radius is roughly 18.5 miles. For Sagittarius A star, it is roughly 7.5 million miles. For M87 star, it is roughly 12 billion miles. For the largest known supermassive black holes, with masses exceeding 50 billion solar masses, the Schwarzschild radius extends beyond the orbit of Pluto. Across this entire range, from objects a few miles across to objects larger than our solar system, the same physics applies, the same event horizon forms, the same interior awaits, and the same singularity is predicted at the center. The tidal forces at the event horizon depend inversely on the mass of the black hole squared. This means that larger black holes have gentler horizons. For a stellar mass black hole, the tidal forces at the horizon are lethal, strong enough to spaghettify a human body well before the crossing. For a supermassive black hole the size of Sagittarius A star, the tidal forces at the horizon are negligible, weaker than the gravitational variation across your body caused by the Earth right now. For the largest supermassive black holes, the event horizon is so gentle that you could set up a physics laboratory there and conduct experiments for hours without detecting anything unusual. The most absolute boundary in the universe is also, for sufficiently large black holes, the most undetectable. This asymmetry between the gentleness of the horizon and the violence of the interior is one of the defining features of black holes. The larger the black hole, the more deceptive the entrance. You would cross the horizon of a supermassive black hole without the slightest indication that anything had changed. No alarm, no sensation, no signal. And yet, from that moment forward, your future would be determined. Every possible path would lead to the center. Every possible effort to escape would be futile. The most absolute prison in the cosmos announces itself with perfect silence. The event horizon also divides the universe into two causally disconnected regions. No signal from inside can reach the outside. No matter can escape. No information can be transmitted outward by any known mechanism. The event horizon is the most permanent, most absolute, most unbreakable barrier in the entire cosmos. No information about the interior can be transmitted to an external observer. This causal disconnection is absolute and permanent. It is not a matter of technology or cleverness. It is a consequence of the geometry of spacetime itself. The light cones, which define the possible future and past of every event, tilt inward at the horizon until every future-directed path leads deeper inside. The event horizon is not a wall that blocks signals. It is a curvature of spacetime that redirects all possible signals inward. The barrier is not physical. It is geometric. This geometric nature of the barrier is what makes it so absolute. A physical wall can, in principle, be breached. A force field can, in principle, be overcome. But a geometric boundary, a boundary defined by the curvature of spacetime itself, cannot be crossed by any physical means. The event horizon is the universe's most perfect prison because it is made not of matter or energy but of the shape of reality itself. The event horizon has a deep connection to the concept of irreversibility. In everyday physics, most processes are reversible at the microscopic level. A movie of billiard balls colliding looks equally valid played forward or backward, but the event horizon introduces a fundamental irreversibility into the structure of spacetime. Crossing the horizon is a one-way process. No amount of energy, no technological advancement, no physical maneuver can reverse it. This irreversibility is not thermodynamic, arising from the statistics of large numbers of particles. It is geometric, built into the structure of spacetime itself. The light cones tilt inward at the horizon. The future points inside. There is no past direction that leads out. The event horizon is the most fundamental source of irreversibility in nature. The concept of the photon sphere, located at 1.5 Schwarzschild radii, illustrates the extreme nature of the spacetime near a black hole. At this distance, photons can orbit the black hole in unstable circular orbits. If you hovered near the photon sphere and looked straight ahead, you would see the back of your own head, the light having traveled all the way around the black hole. Multiple images of the same star would appear at different positions in your visual field, each corresponding to photons that have taken different numbers of orbits. The visual distortions near a black hole are unlike anything in everyday experience, bending, stretching, and multiplying images in a kaleidoscope of curved spacetime. The proper time from the event horizon to the singularity depends on the mass of the black hole. For a non-rotating Schwarzschild black hole, this time is proportional to the mass. For Sagittarius A star, it is roughly 20 seconds. For M87 star, it could be hours. These are the durations of the journey beyond the horizon, the time available for a falling observer to experience the interior before reaching whatever lies at the center. The no-hair theorem states that a black hole is characterized by just three quantities: mass, charge, and spin. All other information about what formed the black hole is hidden behind the event horizon. Two black holes of identical mass, charge, and spin are indistinguishable, even if one was formed from a collapsing star of hydrogen and the other from a star of iron. This radical exterior simplicity implies radical interior complexity. The Bekenstein-Hawking entropy, proportional to the horizon area, tells us that the number of hidden internal states is enormous, roughly 10 to the power of 77 for a solar mass black hole. The thermodynamics of black holes provides crucial constraints on the interior. The four laws of black hole mechanics, established by James Bardeen, Brandon Carter, and Stephen Hawking in the early 1970s, mirror the four laws of thermodynamics. Black holes have genuine temperature, the Hawking temperature, and genuine entropy, the Bekenstein-Hawking entropy. Any description of what lies beyond the event horizon must be consistent with these thermodynamic properties. The exterior has finite temperature, finite entropy, finite energy. The interior must be compatible. The Hawking radiation emitted by the black hole is thermal and featureless, carrying no information about what fell in. If the black hole evaporates completely and the radiation carries no information, all information about the interior is destroyed. This is the information paradox, the most famous problem in modern theoretical physics. Its resolution requires understanding what lies beyond the event horizon in a way that preserves the quantum mechanical principle that information is never destroyed. Observational confirmation came steadily. Cygnus Zone, discovered in 1971, was the first strong black hole candidate. The LIGO Observatory detected gravitational waves from merging black holes in 2015. The Event Horizon Telescope photographed the shadow of M87 star in 2019 and Sagittarius A star in 2022. Andrea Ghez and Reinhard Genzel tracked stars orbiting Sagittarius A star for more than 20 years, sharing the Nobel Prize in 2020. Roughly 90 gravitational wave events have been observed, mostly from black hole mergers. Now, the event horizon has several remarkable properties that are essential for understanding what lies beyond it. The first is that it is invisible to a crossing observer. For a supermassive black hole, the tidal forces at the event horizon are negligible. A freely falling observer would cross the event horizon without feeling anything unusual. No pain, no warning, no alarm. The curvature of space-time at the horizon of Sagittarius A star is gentle, far gentler than the curvature at the surface of a neutron star. The horizon is not a physical barrier. It is a causal boundary, defined not by any local physical effect, but by the global structure of space-time. You cannot detect the horizon by looking at the space-time in your immediate vicinity. You can only detect it by trying to escape and failing. For a stellar mass black hole, the situation is different. The tidal forces at the horizon are extreme, strong enough to tear a human body apart through the process called spaghettification. The smaller the black hole, the more violent the horizon. The gentle crossing is a feature only of large black holes. The second property is gravitational time dilation. As an object approaches the event horizon, time slows down relative to a distant observer. At the horizon itself, time, as measured by the distant observer, stops completely. An outside observer watching you fall toward the event horizon would see you slow down, redshift, grow dimmer, and eventually fade from view, frozen at the edge of the horizon for all eternity. You would never appear to cross. Your image would linger, growing ever fainter, stretching to ever longer wavelengths until it disappeared entirely. But from your own perspective, nothing unusual happens. You cross the horizon in finite time by your own clock. You continue to fall. You experience the interior. Two observers, two completely different realities, both consistent with general relativity, both physically real within their own reference frames. And neither can communicate with the other, because the event horizon prevents any signal from the interior from reaching the exterior. The third property is the no-hair theorem. A black hole is completely characterized by just three quantities: its mass, its charge, and its angular momentum, its spin, nothing else. No matter what formed the black hole, no matter how complex the progenitor star, no matter what the chemical composition or structure of the infalling matter, the final black hole remembers only three numbers. All other information is hidden behind the event horizon. This radical simplicity of the exterior implies radical complexity of the interior. The fourth property is the Bekenstein-Hawking entropy. The entropy of a black hole, a measure of its internal microscopic complexity, is proportional to the area of its event horizon, measured in Planck units. For a solar mass black hole, this entropy is roughly 10 to the power of 77, a number that dwarfs the combined entropy of all non-black hole matter in the observable universe. The black hole has more hidden internal states than everything else in the cosmos combined. The fifth property is Hawking radiation. In 1974, Stephen Hawking showed that black holes emit faint thermal radiation due to quantum effects near the event horizon. This radiation is incredibly weak. The Hawking temperature of a solar mass black hole is roughly 60 billionths of a Kelvin, far colder than the cosmic microwave background at roughly 2.7 Kelvin. The evaporation time for a solar mass black hole is roughly 10 to the power of 67 years, exceeding the current estimated age of the universe by a factor of more than 10 to the power of 56. But the principle matters enormously. The event horizon is not perfectly one-way. It leaks, and this leaking creates the most famous paradox in modern physics, the black hole information paradox. These 5 properties, taken together, paint a picture of an object that is simultaneously simple and complex, transparent and opaque, well understood and deeply mysterious. The exterior is described by just 3 numbers. The interior contains more hidden states than all the visible matter in the universe. The boundary is invisible to a crossing observer, RU, and nothing that crosses can ever return. The density at the event horizon provides an instructive perspective on the nature of the boundary. For a stellar mass black hole of 10 solar masses, the average density at the event horizon is roughly 200 million tons per cubic centimeter. For Sagittarius A star, the density at the horizon is roughly 1,000 kilograms per cubic centimeter, comparable to a heavy metal. For M-87 star, the density at the horizon is less than the density of Earth's atmosphere. The larger the black hole, the more diffuse the matter at its boundary. You could cross the horizon of M-87 star surrounded by space-time less dense than the air you breathe. And yet you would be inside a black hole, falling toward the center, with no possibility of return. This inverse relationship between size and boundary density is one of the most counterintuitive features of black holes. The most massive ones have the gentlest horizons. The door through which you enter is silent and gentle. The destination to which you are carried is the most extreme environment in the universe. The event horizon also has a deep connection to the arrow of time and the thermodynamics of the cosmos. Black holes are the maximum entropy objects for a given mass. The total entropy of all black holes in the observable universe is estimated at roughly 10 to the power of 104, dwarfing the entropy of all non-black hole matter at roughly 10 to the power of 88. The thermodynamic arrow of time points toward black holes. What lies beyond the event horizon is the destination of the arrow, the endpoint of entropy maximization, the thermodynamic fate of the cosmos. The event horizon is connected to the concept of cosmic censorship, proposed by Roger Penrose in 1969. Cosmic censorship states that singularities are always hidden behind event horizons, never visible to the outside universe. If cosmic censorship holds, the breakdown of physics at the center is quarantined. The event horizon serves as a shield, protecting the outside universe from the catastrophe at the center, but cosmic censorship has never been proven, in full generality. Whether singularities can form without event horizons remains an open question. The mathematical structure of the event horizon has been illuminated by the membrane paradigm, developed in the 1980s by Kip Thorne and collaborators. In this framework, the event horizon behaves, for all practical purposes, like a physical membrane with specific physical properties: viscosity, electrical conductivity, temperature. The membrane paradigm provides an intuitive way to understand how the horizon interacts with the outside universe, absorbing matter and radiation, conducting electric charge, vibrating when perturbed. The membrane is not a real physical object, but it captures the essential physics of the horizon in a way that is both intuitive and mathematically precise. The detection of gravitational waves from black hole mergers has provided a new window on the event horizon. When two black holes merge, their event horizons combine to form a single, larger horizon. The merger produces gravitational waves at specific frequencies, determined by the masses and spins of the merging black holes. The ring-down phase, when the merged black hole vibrates, tests the no-hair theorem. The frequencies should be completely determined by the mass and spin of the final black hole. So far, every observation is consistent with general relativity. No deviations have been detected, but future, more sensitive detectors may reveal echoes or anomalies that signal new physics at the horizon. The Event Horizon Telescope has provided direct visual evidence of the event horizon's shadow. The image of M87 star shows a bright ring of emission surrounding a dark shadow. The shadow is the silhouette of the event horizon against the glowing accretion flow. Its size and shape are consistent with the predictions of general relativity for a Kerr black hole. Future observations may resolve the photon ring, a sharp, bright feature just outside the shadow that encodes detailed geometric information about the spacetime near the horizon. These observations tell us about the exterior. They confirm that event horizons exist and that their external properties match the predictions of general relativity, but they tell us nothing about the interior. The event horizon ensures that no information from inside ever reaches the outside. What lies beyond remains the deepest open question in physics. The answer is where the physics becomes deeply strange. These 5 properties define the event horizon. They tell us what it looks like from the outside, but what lies beyond it? What does the interior of a black hole actually look like? What would you experience if you crossed the event horizon and continued to fall? The answer is where the physics becomes deeply strange and deeply unsettling. The concept of the trapped surface, central to Penrose's singularity theorem, deserves further explanation. A trapped surface is a closed, two-dimensional surface from which all outgoing light rays are converging inward. In ordinary spacetime, if you emit light in all directions from the surface of a sphere, the outgoing light rays diverge, spreading outward. But inside an event horizon, the curvature is so extreme that even the outgoing light rays converge. They are all heading inward, toward the center. The existence of a trapped surface is the key technical condition in Penrose's theorem. Once it exists, the singularity is guaranteed. The trapped surface condition is satisfied inside every event horizon. This means that every black hole, every event horizon, contains within it the mathematical guarantee of a singularity, according to general relativity. The guarantee is robust. It does not depend on the specific properties of the collapsing matter. It does not depend on the symmetry of the collapse. It depends only on the existence of the trapped surface and the positivity of energy. These are conditions that are satisfied in every realistic gravitational collapse. The proper time from the event horizon to the singularity provides a concrete measure of the size of the interior. For a Schwarzschild black hole, this time is proportional to the mass. For a solar mass black hole, it is roughly 10 microseconds. For Sagittarius A star, with 4 million solar masses, roughly 20 seconds. For M87 star, with 6.5 billion solar masses, several hours. For the most massive known black holes, with masses exceeding 10 billion solar masses, the time could be many hours. These times define the duration of the journey beyond the event horizon, the window of experience available to a falling observer before reaching whatever lies at the center. The visual experience of the interior has been computed numerically. The falling observer sees the outside universe compressed into a shrinking circle of blue shifted light above, below, darkness. Multiple images of the same stars appear at different positions. The sky is a hall of distorted mirrors. As the fall deepens, the bright circle shrinks and the darkness expands. The perpendicular spatial dimensions contract. The fall dimension stretches. The observer is inside a collapsing universe, heading toward a singularity that general relativity says must be there, but that quantum mechanics says cannot be. What lies beyond the event horizon, according to general relativity, is a region of spacetime unlike anything in ordinary experience. A region where space and time exchange their roles, where the center of the black hole is not a place but a time, where every possible path leads to the same destination, and where, at the end of the journey, the laws of physics themselves break down. Something is wrong with our understanding of what lies beyond this boundary. Something deep and fundamental about the way we think about space, time, and the nature of reality must be revised. The singularity is the proof. The information paradox is the proof. The firewall is the proof. Every paradox and every contradiction that arises at the event horizon is evidence that our current theories are incomplete, that a deeper theory is needed, and that the resolution of these paradoxes will transform our understanding of the universe. To understand this, we must examine what happens to spacetime at the event horizon, and what happens is, by any measure, the most conceptually disturbing prediction in all of physics. Outside the event horizon, spacetime behaves as we expect. You can move freely in 3 dimensions of space, left and right, forward and backward, up and down. And you are carried inexorably forward in 1 dimension of time, from past to future. You can choose where to go in space. You cannot choose to go backward in time. This asymmetry between space and time is one of the deepest features of our experience. At the event horizon, this asymmetry breaks in a spectacular way. Inside the black hole, the radial direction, the direction pointing toward the center, acquires the mathematical character of time. And what was the time direction outside becomes a spatial direction inside. The coordinates literally switch. The metric tensor, the mathematical object that encodes the geometry of space-time, changes the signs of its temporal and radial components at the horizon. The center of the black hole, the singularity, is not a place in space. It is a moment in time, a moment in your future, as inevitable as next Wednesday, as unavoidable as tomorrow. You cannot steer around it. You cannot fly away from it. You cannot even slow your approach to it, because you are not approaching it through space. You are approaching it through time. And time, inside or outside a black hole, always moves forward. Let that sink in. Every path inside the black hole leads to the singularity, not because the singularity is in every direction in space, but because it is in the one direction you cannot avoid, the future. Trying to avoid the singularity inside a black hole is exactly as meaningful as trying to avoid next Thursday. You can go left or right, up or down, but you cannot go backward in time. And the singularity is in the future. There is a cruel additional feature. Firing your rockets inside a non-rotating black hole does not help you avoid the singularity. It actually reduces your remaining proper time before reaching it. The optimal strategy for maximizing your survival time inside a Schwarzschild black hole is to do nothing, to fall freely, to accept the inevitable. Every expenditure of energy, every attempt to change course, brings the singularity closer in time. The universe has designed the interior so that struggle is not just futile, but counterproductive. For a supermassive black hole, the proper time from the event horizon to the singularity can be substantial. For Sagittarius A star, with roughly 4 million solar masses, it is on the order of 20 seconds. For M87 star, with 6.5 billion solar masses, it could be hours. Hours of consciousness inside a black hole, aware and thinking, falling toward a destination that physics cannot describe, with nothing to do but observe and wait. What would you see during this fall? The visual experience has been computed numerically by several research groups, and the results are extraordinary. Looking outward, toward the event horizon you crossed, you would see the outside universe. But it would be compressed and distorted. The light from distant stars blue-shifted to higher energies, crowded into a shrinking circle above you. Looking inward, toward the singularity, you would see darkness. Not the darkness of empty space, but the darkness of a future from which no light can reach you. The sky above brightens and shrinks. The darkness below expands. Multiple images of the same stars appear at different positions, each corresponding to photons that have taken different paths through the curved spacetime. The visual field is a hall of mirrors, distorted and evolving continuously as you fall deeper. The spatial dimensions perpendicular to your fall contract. The dimension along your fall stretches. You are inside a universe that is collapsing around you, a cosmology in miniature, contracting toward a future singularity rather than expanding away from a past one. The mathematics of the Schwarzschild interior is closely related to the mathematics of cosmological models. The interior of a black hole is, in a precise mathematical sense, a universe in reverse. The information paradox is not just a problem about information. It is a problem about the nature of the event horizon and the interior. If information is preserved during evaporation, as most physicists now believe, then something about the classical picture of the interior must be wrong. The smooth, featureless event horizon described by general relativity must be modified, either subtly or dramatically, to allow information to escape. Hawking himself conceded in 2004 that information is likely preserved, awarding a baseball encyclopedia to John Preskill. But the concession did not explain the mechanism. The how remains one of the great unsolved problems. The island formula, developed in 2019 and 2020, provided the most significant recent progress. It showed that the entropy of Hawking radiation follows the Page curve, the specific pattern that characterizes unitary evaporation. The calculation includes quantum extremal islands, regions of the black hole interior that are effectively owned by the radiation. This blurs the classical distinction between inside and outside. Parts of the interior, according to this calculation, belong to the exterior. The boundary between inside and outside is not as sharp as classical physics suggests. This has profound implications for what lies beyond the event horizon. If regions of the interior can be quantum mechanically connected to the exterior radiation, then the interior is not isolated. It is entangled with the outside. It is connected to the radiation through quantum correlations that transcend the classical event horizon. What lies beyond the horizon is not a sealed room, but a quantum system in constant, hidden communication with the outside through the subtle correlations of entanglement. The cosmic censorship conjecture, proposed by Roger Penrose in 1969, states that singularities are always hidden behind event horizons. If cosmic censorship holds, the breakdown of physics at the center is quarantined. The madness stays inside. The outside universe remains predictable. But cosmic censorship has never been proven in full generality. Its status remains one of the great open questions in mathematical physics. The Penrose process, described by Penrose in 1969, shows that energy can be extracted from a rotating black hole through its ergosphere, the region outside the event horizon where spacetime is dragged around by the black hole's rotation. For a maximally spinning black hole, up to roughly 29% of the total mass energy can be extracted. This reveals that black holes are not passive objects. They are dynamic, thermodynamic systems. What lies beyond the event horizon is the interior of a thermodynamic engine, and the properties of that interior must be consistent with the engine's thermodynamic behavior. The relationship between the exterior thermodynamics and the interior structure is one of the tightest constraints available. The Bekenstein-Hawking entropy tells us the number of internal microstates. The Hawking temperature tells us the thermal properties. The four laws of black hole mechanics tell us how the system responds to perturbations. Any model of the interior must reproduce all of these external properties. This constraint eliminates many naive proposals and narrows the range of viable answers. The connection between quantum mechanics and general relativity at the event horizon has been further illuminated by the concept of scrambling. When information crosses the event horizon, it is rapidly scrambled and distributed across the entire horizon. The scrambling time for Sagittarius A star is on the order of milliseconds. Within thousandths of a second, the information has been processed, entangled with everything else in the system, and distributed across the boundary. Patrick Hayden and John Preskill showed in 2007 that black holes are the fastest scramblers in nature. What lies beyond the horizon is the fastest information processor in the universe. The Margolis-Levitin theorem sets a fundamental limit on how fast any quantum system can evolve between orthogonal states. Black holes saturate this limit. They process information at the maximum rate allowed by quantum mechanics. The interior is not a passive container. It is an active computation running at the physical limits of information processing. As you approach the singularity, the tidal forces grow. For a supermassive black hole, they are negligible at the horizon and increase gradually, becoming perceptible only in the final moments. The rate of increase accelerates. The forces double and redouble in ever shorter intervals. In the last fraction of a second, the tidal forces exceed the binding energy of atoms, then nuclei, then nucleons. Every structure at every scale is torn apart. Near the singularity, the geometry of spacetime oscillates chaotically. These are the BKL oscillations, named after Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz. Space contracts in one direction while expanding in another, then switches, contracts differently, expands differently. The oscillations become faster and more violent as the singularity is approached, their frequency approaching infinity. Charles Misner called this mixmaster dynamics. The approach to the singularity is not gentle. It is violent, chaotic, and increasingly frenzied. The geometry writhes and convulses in a pattern of ever-increasing complexity. And then the mathematics breaks. The curvature diverges to infinity. The density diverges to infinity. The tidal forces become infinite. Every physical quantity the theory can compute produces infinity. The geodesics, the paths of particles through space-time, simply terminate. Not at a wall, not at a barrier. They just end. The space-time ceases to be defined. The physics stops. This is the singularity, and it is here that general relativity fails. But here is the problem. Most physicists do not believe the singularity is real. They believe it is a signal, a warning, a mathematical artifact of a classical theory applied beyond its domain of validity. At the singularity, the curvature reaches the Planck scale, roughly 10 to the power of negative 35 meters, where quantum effects of gravity must become important. General relativity ignores quantum mechanics entirely. Quantum mechanics ignores gravity. The singularity is where their mutual ignorance becomes catastrophic. The theory that would resolve this, quantum gravity, does not yet exist in a complete form. We have candidates: string theory, loop quantum gravity, the holographic principle, causal set theory, asymptotic safety. Each proposes a different picture of what replaces the singularity. None has been confirmed by experiment. The Planck scale is roughly 17 orders of magnitude beyond the reach of our most powerful particle accelerators. Direct experimental verification is, for now, impossible. This means that the question, what lies beyond the event horizon, has two answers. The classical answer, provided by general relativity, says a region of inverted spacetime, a collapsing geometry, a chaotic approach to a singularity of infinite density. The quantum answer, provided by no single theory but suggested by all of them, says the singularity is resolved at the Planck scale, replaced by something finite, something quantum, something we do not yet fully understand. And it gets worse, because the problems with the interior of a black hole do not end at the singularity. They begin at the event horizon itself. The information paradox, discovered by Hawking in 1974, arises because the Hawking radiation emitted by the black hole is thermal, featureless, and carries no information about what fell in. If the black hole evaporates completely, all the information about everything that ever crossed the event horizon is permanently destroyed. This violates unitarity, the quantum mechanical principle that information is always preserved. Most physicists now believe information is preserved. Hawking himself conceded a bet with John Preskill in 2004. But if information is preserved, then something about the event horizon, or the interior, or both, must be different from what general relativity predicts. The smooth, featureless crossing that general relativity describes may not be the full story. The interior may be more complex, more structured, more fundamentally quantum than the classical picture suggests. The classical picture, the smooth, collapsing spacetime with a singularity at the center, may be only the first approximation. The quantum corrections, which general relativity ignores, may transform the interior in ways we cannot yet predict. The singularity may be replaced by a bounce. The smooth horizon may be replaced by a firewall. The empty interior may be replaced by a fuzzball. The three-dimensional geometry may dissolve into quantum information. We do not yet know which of these possibilities is correct, but we know that the classical picture is incomplete. The firewall paradox, introduced in 2012 by Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully, sharpened this crisis. The AMPS argument showed that three cherished principles, unitarity, the equivalence principle, and the validity of quantum field theory, cannot all hold at the event horizon of an old black hole. If unitarity and quantum field theory hold, the horizon becomes a firewall, a wall of Planck energy radiation that destroys everything crossing it. The smooth crossing is replaced by instant annihilation. The Penrose process, described by Roger Penrose in 1969, reveals that the region just outside the event horizon of a rotating black hole, the ergosphere, has remarkable properties. Within the ergosphere, space-time is dragged around by the black hole's rotation so violently that no object can remain stationary. Everything must co-rotate. Energy can be extracted from the ergosphere by a clever splitting process, in which one piece of an object falls into the black hole on a negative energy trajectory, while the other escapes with more energy than the original. For a maximally spinning black hole, up to roughly 29% of the total mass energy can be extracted this way. The ergosphere tells us that what lies beyond the event horizon is part of a dynamic system, a thermodynamic engine that can do work on the outside universe. The 4 laws of black hole mechanics established by Bardeen, Carter, and Hawking mirror the 4 laws of thermodynamics exactly. Black holes have temperature, the Hawking temperature. They have entropy, the Bekenstein-Hawking entropy. They obey thermodynamic laws. Whatever lies beyond the event horizon must be consistent with these thermodynamic properties. This means that what lies beyond the event horizon depends on which principles of physics you trust most. If you trust general relativity, the interior is a smooth, collapsing spacetime leading to a singularity. If you trust quantum mechanics, the interior may not exist at all, or may be radically different from the classical picture. The event horizon is the battlefield where our 2 greatest theories fight, and the winner determines what the interior looks like. But here is what makes this truly terrifying. We cannot look behind the horizon to check. The event horizon ensures that no information about the interior reaches the outside universe. We must rely entirely on theory, and the theories disagree. The experience of the interior for a falling observer in a supermassive black hole would be unlike anything in ordinary experience. After crossing the event horizon without noticing, the observer would find themselves in a region where the radial direction has become time-like, and the time direction has become space-like. This means that the center of the black hole is not below them. It is in front of them in time. It is in their future. And every direction they look, every way they try to move, every path they consider, leads toward it. The contracting geometry would become perceptible gradually. The spatial dimensions perpendicular to the fall would begin to squeeze. The dimension along the fall would stretch. The tidal forces, negligible at the horizon, would grow, slowly at first, then with increasing speed. The observer would have seconds, minutes, or hours, depending on the mass of the black hole, before the tidal forces became uncomfortable, then painful, then lethal, then beyond anything human experience can describe. Looking outward during the fall, the observer would see the external universe compressed into a bright disk above them. The light from the stars blue-shifted to higher energies. The image is distorted and multiplied by the curvature. Looking inward, they would see only darkness, the darkness of a future they cannot avoid. The visual experience would be profoundly disorienting, a constantly evolving kaleidoscope of distorted starlight above and absolute darkness below. The BKL dynamics would set in near the center. The geometry would begin to oscillate chaotically, contracting in one direction while expanding in another, switching directions with increasing speed and violence. The approach to the singularity would not be smooth or orderly. It would be a frenzy of geometric distortion, a convulsion of space-time, growing more extreme and more rapid with each passing moment. The observer would be torn apart by forces that change direction faster than neurons can fire, in a geometry that writhes and convulses toward infinite curvature. And then the mathematics stops. The equations produce infinity. The geodesics terminate. The space-time ceases to be defined. What happens at this point is unknown. General relativity says the singularity is reached, a point of infinite density and zero volume where all physical quantities diverge. Quantum mechanics says this cannot be correct, that the uncertainty principle forbids infinite compression, that unitarity forbids the destruction of information, that the Bekenstein-Hawking entropy demands finite internal structure. Quantum gravity, whatever form it takes, must resolve this contradiction. The resolution will determine what truly lies at the center, beyond the event horizon, at the end of the journey. The truth lies in a theory we do not yet possess. But every candidate for that theory agrees on one point. The singularity is not real. It is a placeholder, a signal, a warning that the classical theory has exceeded its domain. Infinite density does not occur in nature. The Planck scale sets a flaw. Something finite, something quantum, something we do not yet fully understand, replaces the classical prediction of infinity. The difference between the interior of a non-rotating Schwarzschild black hole and a rotating Kerr black hole is dramatic. The Kerr interior has two horizons, an outer event horizon and an inner Cauchy horizon. Between them, space and time are inverted, as in the Schwarzschild case. But at the inner horizon, they revert. Beyond the inner horizon, the singularity is a ring rather than a point, and the Kerr mathematics formally permits paths through the ring into entirely different spacetimes. However, the inner Cauchy horizon is almost certainly unstable. The mass inflation instability, first identified by Werner Israel and Eric Poisson, shows that even tiny amounts of infalling radiation are blue-shifted to arbitrarily high energies at the Cauchy horizon. The curvature diverges. The inner horizon is replaced by a singularity. The beautiful mathematical structure of the Kerr interior, with its ring singularity and alternate universes, is destroyed by the accumulated perturbation of billions of years of infalling radiation. The actual interior of a real rotating black hole is messier, more violent, and less understood than the idealized Kerr solution suggests. What this means for what lies beyond the event horizon is that we cannot simply read off the answer from the classical solutions. The Schwarzschild interior and the Kerr interior are mathematical idealizations that capture some features of reality but miss others. The true interior, the one that incorporates both general relativity and quantum mechanics, the one that resolves the singularity and preserves information, is described by a theory we do not yet have. The BKL dynamics near the singularity reveal the extraordinary violence of the approach to the center. Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz showed that near a generic singularity, the geometry of spacetime oscillates chaotically. Space contracts in one direction while expanding in another, then switches. The oscillations become faster and more violent as the singularity is approached, their frequency approaching infinity. Charles Misner named this mixmaster dynamics. Each spatial point approaches the singularity independently, on its own chaotic trajectory. The interior of a real black hole near its singularity is not a simple collapse to a point. It is a maelstrom of geometric distortion, a convulsion of spacetime that grows without bound. The connection between the singularity and the initial singularity of cosmological models is worth noting. Many cosmological models predict a singularity at the beginning of cosmic history, a moment of infinite density from which the universe expanded. This initial singularity shares mathematical properties with the singularity at the center of a black hole. Both are points where general relativity predicts infinite curvature. Both are presumably resolved by quantum gravity. The techniques developed for one often apply to the other. Loop quantum cosmology, which replaces the initial singularity with a quantum bounce, uses the same methods that loop quantum gravity applies to the black hole singularity. The fate of what lies at the center of a black hole may be intimately connected to the origin of the cosmos. The Heisenberg uncertainty principle provides the most direct quantum mechanical argument against the singularity. At the singularity, matter is compressed into zero volume, meaning its position is known with infinite precision. But the uncertainty principle says that if position is known exactly, momentum must be completely uncertain, implying infinite kinetic energy and infinite pressure resisting further compression. The quantum pressure generated by the uncertainty principle should prevent matter from reaching infinite density. The collapse should halt at the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, an enormous number but critically not infinity. Unitarity provides another fundamental argument. The laws of quantum mechanics are reversible. The present always contains a complete record of the past. Information is never destroyed. But the singularity, where physics breaks down, would destroy information. The quantum state of everything that fell in, would be compressed into a point where the equations produce infinity and the physics ceases to function. If the singularity is real, information is destroyed. If information is preserved, the singularity cannot be real. Most physicists now believe information is preserved, which means the singularity must be replaced by something that preserves it. The Bekenstein-Hawking entropy provides a quantitative constraint. The entropy of a solar mass black hole is roughly 10 to the power of 77. This means the interior has an enormous number of microscopic states. Any replacement for the singularity must accommodate this vast number of configurations. A true singularity, a point of zero volume, has no room for microstates. The entropy demands internal structure. The singularity denies it. The third law of thermodynamics requires that entropy be well defined. The Hawking temperature requires that temperature be finite. The four laws of black hole mechanics require specific thermodynamic relationships. Every thermodynamic constraint points in the same direction. The singularity is not real. Something finite and well-defined must take its place. The firewall paradox, introduced in 2012 by Almheri, Marolf, Polchinski, and Sully, brought the conflict to its sharpest point. Three principles: unitarity, the equivalence principle, and the validity of quantum field theory, cannot all hold at the horizon of an old black hole. If unitarity holds, the smooth horizon may be replaced by a firewall, a wall of Planck energy radiation. This would mean that what lies beyond the event horizon, for an old black hole, is not a smooth interior but instant destruction. The classical picture of the interior would be entirely wrong. The ER equals EPR conjecture, proposed by Susskind and Maldacena in 2013, offers a resolution that preserves the smooth horizon through a network of microscopic wormholes connecting entangled particles. If correct, what lies beyond the event horizon is a space-time threaded with quantum wormholes, connected to the exterior through entanglement, with the singularity replaced by a hub of quantum connectivity. Black hole complementarity says the answer depends on who asks. The outside observer sees no interior. The falling observer sees an interior. Both are correct. The interior exists and does not exist, depending on the observer. This radical observer dependence of reality is one of the most disturbing implications of the entire program. The disagreement between the theories is not a minor technical discrepancy. It is a fundamental clash between two incompatible pictures of reality. General relativity says the event horizon is smooth and the interior is a collapsing spacetime. Quantum mechanics says the smooth horizon may be a firewall. General relativity says the singularity is the endpoint. Quantum mechanics says the singularity cannot exist. General relativity says the interior is a fixed region of spacetime. Quantum mechanics, through the holographic principle, says the interior is a projection of boundary physics. General relativity says crossing the horizon is irreversible. The island formula says parts of the interior belong to the exterior radiation. Each theory is extraordinarily well tested in its own domain. General relativity has been confirmed by gravitational wave observations, by black hole shadow images, by the precession of Mercury, by gravitational lensing, by time dilation measurements on satellites. Quantum mechanics has been confirmed by atomic spectroscopy, by particle physics experiments, by the functioning of every semiconductor and laser and MRI machine on Earth. Both theories work. Both have been validated to extraordinary precision, and they disagree about what lies beyond the event horizon. The resolution requires a theory of quantum gravity, a theory that unifies both frameworks into a single consistent picture. Every candidate for quantum gravity, string theory, loop quantum gravity, holographic duality, causal set theory, asymptotic safety, agrees that the singularity is resolved. The mechanisms differ. The details differ, but the conclusion is universal. Infinite density does not occur. Something finite replaces it, and whatever that something is, it determines what truly lies beyond the event horizon. The Planck scale, roughly 10 to the power of negative 35 meters, is the arena where this resolution occurs. At this scale, quantum gravitational effects dominate. The smooth spacetime of general relativity dissolves. something else takes over. The gap between this scale and our experimental capabilities is roughly 17 orders of magnitude, a chasm that no foreseeable technology can bridge directly. We must rely on theory, on mathematical consistency, on astrophysical observations that provide indirect constraints. The thermodynamic constraints are among the most powerful tools available. The Bekenstein-Hawking entropy assigns a finite, well-defined entropy to every black hole. The Hawking temperature assigns a finite temperature. The four laws of black hole mechanics provide specific relationships between mass, area, angular momentum, and charge. Any description of what lies beyond the horizon must reproduce all of these thermodynamic properties. The exterior thermodynamics constrains the interior structure. The connection between the singularity and the information paradox is direct. If the singularity destroys information, unitarity is violated. If unitarity is preserved, the singularity must be replaced by something that preserves information. The fate of the singularity and the fate of information are the same problem. Resolving one resolves the other. The scrambling time of a black hole, the time it takes for infalling information to be distributed across the entire horizon, is on the order of milliseconds for Sagittarius A star. The Margolis-Levitin theorem sets the maximum rate of quantum evolution for a system of given energy, and black holes saturate this bound. What lies beyond the horizon is not a passive void, but the fastest information processor in nature, operating at the absolute physical limits of quantum mechanics. The question of what lies beyond the event horizon has generated some of the most creative, radical, and fiercely debated proposals in the history of physics. Each proposal offers a different vision of the interior, and each reveals something profound about the nature of reality. What follows is a journey through the most important of these proposals. The first proposal is the classical general relativistic interior. According to general relativity alone, without quantum corrections, the interior of a non-rotating black hole is a smooth, collapsing spacetime that terminates at a singularity. The falling observer crosses the horizon without incident, experiences the inversion of space and time, falls through a contracting geometry for a finite proper time, and is destroyed at the singularity. This is the textbook answer. It is mathematically precise, and most physicists believe it is incomplete. For a rotating black hole, described by the Kerr solution found by Roy Kerr in 1963, the interior is far more elaborate. The Kerr black hole has two horizons, an outer event horizon and an inner Cauchy horizon. Between them, space and time are inverted. Beyond the inner horizon, they revert to their normal roles. The singularity is a ring rather than a point. The Kerr mathematics formally permits paths through the ring into entirely different spacetimes, different universes, with different physical properties, but the inner Cauchy horizon is almost certainly unstable. The mass inflation instability, demonstrated by Werner Israel and Eric Poisson in the late 1980s, shows that infalling radiation is blue-shifted to arbitrarily high energies at the inner horizon, creating a singularity. The elegant Kerr interior is a mathematical idealization that does not survive contact with the messy reality of actual black holes. The wormholes and alternate universes predicted by the Kerr solution are almost certainly fictional. The second proposal is the fuzzball, developed within string theory by Samir Mathur and collaborators. In the fuzzball picture, the entire classical interior is replaced by a complicated quantum gravitational structure made of strings and higher dimensional brains. There is no event horizon in the traditional sense. There is no empty interior. There is no singularity. The black hole is a ball of stringy material extending to where the horizon would be. Each fuzzball configuration corresponds to a different microstate. For a solar mass black hole, the number of microstates is 10 to the power of 77, matching the Bekenstein-Hawking entropy exactly. The fuzzball surface radiates, carrying information about the microstate, and the information paradox does not arise. The singularity is eliminated entirely. But the fuzzball violates the equivalence principle. A falling observer would encounter the fuzzball surface before crossing the would-be horizon. The smooth crossing predicted by general relativity is replaced by an interaction with a quantum gravitational boundary. Whether this is a feature or a bug is debated. The numbers are striking. For Sagittarius A star, with roughly 4 million solar masses, the Bekenstein-Hawking entropy is roughly 10 to the power of 87. The number of fuzzball microstates is 10 to the power of 10 to the power of 87. This number is so vast that it defies comprehension. Each microstate is a different geometric configuration. Each radiates differently. The internal complexity behind the horizon is staggering. The third proposal is the quantum bounce of loop quantum gravity. In this framework, spacetime is discrete at the Planck scale. When matter collapses to the Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, the discrete structure generates a quantum gravitational pressure that halts the collapse. The matter bounces. The singularity is replaced by a Planck-scale core of maximum but finite density. The bounce may connect the black hole to a white hole, a time-reversed black hole from which matter emerges rather than falling in. The work of Hal Haggard and Carlo Rovelli, published in 2014, explored this transition in detail. The matter that collapsed to form the black hole reaches maximum density, bounces, and eventually re-emerges as a white hole. The singularity is replaced by a quantum bridge connecting collapse and expansion. In this picture, what lies beyond the event horizon is not a dead end, it is a passage. A tunnel through Planck-scale physics from black hole to white hole, from collapse to expansion, from past to future, and through a quantum transition that connects them. The interior is not eternal. It is temporary. The black hole is a temporary state, eventually transitioning to a white hole that releases everything that fell in. The fourth proposal comes from the holographic principle and ADS, CFT. In the ADS, CFT framework, discovered by Juan Maldacena in 1997, a theory of gravity in anti-de Sitter space is exactly equivalent to a quantum field theory on its boundary. The boundary theory is well-defined, unitary, and singularity-free. Whatever appears as a singularity in the bulk is smooth and finite in the boundary. The Penrose-Hawking singularity theorems guarantee that some kind of singularity exists behind every event horizon, assuming general relativity is correct and energy conditions are satisfied. But the theorems do not specify the nature of the singularity. They say geodesics must be incomplete. They do not say what the incomplete geodesics encounter at their termination point. The theorems guarantee the disease but not the symptoms. This leaves room for quantum gravity to resolve the singularity without violating the theorems. If quantum effects modify the geometry at the Planck scale, the geodesics might terminate not at a point of infinite density but at a region of Planck-scale physics where the classical description fails and a quantum description takes over. The geodesics are still incomplete in the classical sense, satisfying the theorems, but the physical reality at their termination is finite and well-defined, not singular. The convergence of all approaches on the Planck scale is powerful evidence. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is the natural scale at which quantum gravitational effects dominate. Every serious approach to quantum gravity identifies this scale as the resolution point. The specific mechanisms differ, but the conclusion is universal. The gravitational path integral provides additional insight. When all possible spacetime geometries are summed over, including replica wormholes and other exotic contributions, the result is finite and unitary. The singularity, present in individual classical geometries, is washed out in the quantum sum. The full quantum theory may be singularity-free, even though its classical limit contains singularities. The thermodynamic constraints from the Bekenstein-Hawking entropy, the Hawking temperature, and the four laws of black hole mechanics provide independent checks. Any resolution of the interior must reproduce these external thermodynamic properties. The constraints are tight and eliminate many proposals. The observational constraints from gravitational wave astronomy and the Event Horizon Telescope are tightening with each new detection. Each black hole merger provides a test of general relativity in the strong field regime. The ring-down signals test the no-hair theorem. Future detectors, including LISA, the Einstein Telescope, and Cosmic Explorer, will provide orders of magnitude improvements in sensitivity. The photon ring, A sharp, bright feature near the event horizon encodes detailed information about the near-horizon spacetime geometry. If quantum gravity modifies this geometry, future observations might detect the modification. Each observation narrows the space of possible answers. Each constrains the theories. The gap between what we can observe and what we can calculate is closing, slowly but measurably. Each gravitational wave detection constrains the strong field behavior of gravity. Each event horizon telescope image constrains the near-horizon geometry. Each theoretical advance narrows the range of possible quantum gravity theories. The convergence of independent lines of evidence, from string theory to loop quantum gravity to holographic duality to the gravitational path integral, provides confidence that the singularity is resolved at the Planck scale, even without direct experimental verification. The question of what lies beyond the event horizon, which once seemed permanently unanswerable, is being approached from both the theoretical and observational sides. When the two sides meet, the answer will be found. Each black hole merger detected by LIGO and Virgo tests general relativity in the strong field regime. The ring-down signals test the no-hair theorem. Future detectors may detect echoes or anomalies that signal new physics near the horizon. The Event Horizon Telescope may resolve the photon ring, encoding information about the near-horizon geometry. Space-based detectors like LISA will detect supermassive black hole mergers. Each observation constrains the range of viable theories. Each narrows the space of possible answers to what lies beyond the event horizon. The gap between theory and observation is narrowing, and when the two meet, the question will finally have an answer. The holographic principle suggests that the three-dimensional interior of the black hole is a projection of two-dimensional boundary physics. The interior, including the singularity, is not independently real. It is derived from the boundary. It is a holographic image, an emergent phenomenon that breaks down at extreme curvatures. What lies beyond the event horizon is a holographic projection that normally works well but that fails at the center, where the projection loses coherence and the underlying quantum reality shows through. The island formula, developed in 2019 and 2020, showed that the entropy of Hawking radiation follows the Page curve, confirming that information is preserved during evaporation. The calculation includes quantum extremal islands, regions of the interior that are effectively part of the radiation rather than the black hole. This suggests that the interior is not as sharply separated from the exterior as classical physics implies. The boundary between inside and outside is blurred by quantum effects. The fifth proposal is the firewall. If the AMPS argument is correct, what lies beyond the event horizon of an old black hole is not a smooth spacetime, but a wall of Planck energy radiation at or near the horizon. Anything crossing the horizon is instantly destroyed. The classical interior does not exist. There is no journey to the singularity. There is only annihilation at the boundary. The relationship between the event horizon and quantum entanglement is one of the deepest discoveries of modern physics. The smooth vacuum state at the event horizon is maintained by quantum entanglement between modes just inside and just outside the horizon. This entanglement is what makes the horizon feel smooth and unremarkable to a crossing observer. If this entanglement is disrupted, the smooth vacuum is destroyed, and the horizon becomes a firewall, a wall of high-energy radiation. The AMPS firewall argument shows that this entanglement cannot be maintained simultaneously with the entanglement required for unitarity. For an old black hole, one that has radiated away more than half its entropy, the late Hawking radiation must be entangled with the early radiation to preserve information. But it must also be entangled with the interior to maintain the smooth horizon. The monogamy of entanglement forbids both. Something must give. This conflict between entanglement requirements is at the heart of the modern understanding of what lies beyond the event horizon. The smooth interior predicted by general relativity depends on a specific pattern of entanglement that may not be sustainable for old black holes. What lies beyond the horizon of an old black hole may be fundamentally different from what lies beyond the horizon of a young one. The firewall arises because the monogamy of entanglement prevents the late Hawking radiation from being simultaneously entangled with both the early radiation, as unitarity requires, and the interior. As the smooth horizon requires, one entanglement must break. If the interior entanglement breaks, the smooth vacuum at the horizon is disrupted. The result is a high-energy wall that destroys all infalling matter. The sixth proposal is ER equals EPR, offered by Leonard Susskind and Juan Maldacena in 2013. This conjecture says that quantum entanglement and wormholes are the same phenomenon. Every pair of entangled particles is connected by a microscopic wormhole. The smooth horizon is maintained by a network of wormholes connecting the interior to the exterior. What lies beyond the event horizon is a space-time threaded with wormholes, connected to the outside through quantum entanglement. If ER equals EPR is correct, the interior is not isolated. It is quantum mechanically connected to the exterior through the entanglement structure of the Hawking radiation. The singularity might be replaced by a confluence of wormhole geometry, a hub of quantum connectivity rather than a point of infinite density. The seventh proposal is black hole complementarity, introduced by Leonard Susskind, Lars Thorlacius, and John Uglum in 1993. Complementarity states that the interior and exterior descriptions are both valid, but complementary. The outside observer sees information processed on the horizon and returned in Hawking radiation. The falling observer sees a smooth interior and a journey to the singularity. Both are correct. Neither is complete. No single observer can verify both. If complementarity is correct, then what lies beyond the event horizon depends on who is asking. For the falling observer, the interior is whatever quantum gravity says it is. For the outside observer, there is no interior. All the physics happens on the horizon. The inside is a complementary description, not an independently existing region. The eighth proposal involves the gravitational path integral and replica wormholes. Recent work by Geoffrey Pennington, Ahmed Almheri, and others showed that the gravitational path integral, which sums over all possible spacetime geometries, naturally includes contributions from replica wormholes. These contributions reproduce the page curve and ensure unitarity. The singularity, present in individual classical geometries, is averaged away in the quantum sum. The full quantum theory is singularity-free. The math is striking. Every approach, from every direction, converges on the same conclusion. The classical interior predicted by general relativity is incomplete. The singularity is not real. The smooth crossing may not be the whole story. What lies beyond the event horizon is something more complex, more quantum, more deeply structured than the classical picture suggests. The convergence across independent approaches is the strongest theoretical evidence we have about the interior of a black hole. String theory, loop quantum gravity, holographic duality, quantum error correction, computational complexity, the gravitational path integral, all converge on the Planck scale as the resolution point. The specific mechanisms differ, but the conclusion is universal. Infinite density does not occur. Something finite replaces the singularity. The thermodynamic constraints from the Bekenstein-Hawking entropy, the Hawking temperature, and the four laws of black hole mechanics provide independent checks on every proposal. The exterior has finite, well-defined thermodynamic properties. Any description of the interior must be consistent with these properties. A true singularity, with infinite density and undefined thermodynamics, is inconsistent with the finite exterior thermodynamics. Something finite must replace it. The thermodynamics demands it. The Penrose process shows that energy can be extracted from rotating black holes through the ergosphere. For a maximally spinning black hole, up to roughly 29% of the mass energy is extractable. This reveals that what lies beyond the event horizon is part of a dynamic thermodynamic system, not a static void. The interior is connected to the exterior through the engine of accretion and extraction. The properties of the interior constrain the behavior of the engine. And this is where the answer becomes deeply unsettling, because the convergence tells us what, it does not tell us how. The destination is glimpsed, the path is unknown. The convergence of all approaches on the Planck scale as the resolution point for the singularity is one of the most important theoretical results available. String theory identifies the string length as the minimum scale. Loop quantum gravity identifies the Planck volume as the minimum discrete unit. Causal set theory identifies the fundamental causal element. Asymptotic safety identifies the ultraviolet fixed point. Each approach, from a different starting point and with different mathematical tools, arrives at the same conclusion. The singularity is resolved at or near the Planck scale. The Planck density, roughly 5.1 times 10 to the power of 96 kilograms per cubic meter, is the natural density at which quantum gravitational effects dominate. It exceeds nuclear density by roughly 78 orders of magnitude. It exceeds the density achievable in the most powerful particle accelerators by a similar amount. The gap between our experimental reach and the Planck scale is immense, but the theoretical convergence is strong. This convergence gives confidence that the singularity is not real, even in the absence of direct experimental verification. When independent theoretical approaches agree, the probability that they are all wrong is small. The singularity is almost certainly replaced by something finite at the Planck scale. The gravitational path integral provides additional support. When all possible space-time geometries are summed over, including exotic contributions from replica wormholes, the result is finite and unitary. The singularity, present in individual classical geometries, is washed out in the quantum sum. The quantum theory is singularity-free. This result is one of the most significant in recent quantum gravity research. It shows that the singularity is not a physical entity but a classical artifact, washed away by the quantum sum over geometries. The full quantum theory, when computed correctly, produces no infinities, no breakdown, no singularity. What lies beyond the event horizon, according to the quantum path integral, is finite and well-defined, even at the center. String theory's approach to the singularity goes beyond the fuzzball proposal. In certain string theoretic models, the singularity is resolved by the extended nature of strings. Point particles can be compressed to zero size and infinite density, but strings cannot be compressed below their fundamental length. The string length, roughly the Planck length, sets a minimum scale. Below this scale, the classical concept of space-time geometry breaks down and the full string theoretic physics takes over. The singularity is not softened or regularized. It is replaced by a regime where geometry itself loses meaning and a new stringy description is needed. The ADS CFT correspondence, discovered by Maldacena in 1997, provides the most powerful framework for studying what lies beyond the event horizon. In this framework, a gravitational theory in the bulk of anti-de Sitter space is exactly equivalent to a non-gravitational quantum field theory on the boundary. The boundary theory is well-defined, unitary, and singularity-free. Whatever appears as a singularity in the bulk has a smooth, finite description on the boundary. The singularity is an artifact of the bulk geometric description, not a feature of the fundamental physics. Within AD-CFT, the Bekenstein-Hawking entropy is exactly the logarithm of the number of boundary microstates. Information is preserved because the boundary theory is unitary. The Page curve has been derived from gravitational calculations using the island formula. The evidence for information preservation within this framework is overwhelming. But ADS-CFT applies to anti-de Sitter space, which has a negative cosmological constant. Our universe has a positive cosmological constant. Whether holographic duality extends to our universe remains an open question. This is perhaps the most important limitation of the most powerful framework we have for studying the interior of black holes. The quantum error correction perspective, developed by Harlow, Pastovsky, Yoshida, Preskill, and others, reveals that the holographic encoding of the bulk in the boundary has the mathematical structure of an error-correcting code. The bulk geometry is redundantly encoded, protected against local disturbances. Near the singularity, the code degrades. The geometric description becomes unreliable. At the singularity, the code has broken down completely. What lies beyond the event horizon, at the deepest level, is a region where the geometric code fails and the fundamental quantum information requires a different kind of description. The island formula showed that the entropy of Hawking radiation follows the Page curve. This was derived by including quantum extremal islands, regions of the interior that are effectively part of the radiation. This calculation blurs the classical boundary between inside and outside. The interior is not sharply separated from the exterior. Quantum entanglement connects them. Parts of the interior belong, informationally, to the radiation. The classical event horizon, which seems so absolute from the general relativistic perspective, is quantum mechanically porous. Suskind's computational complexity proposal adds temporal depth. The interior volume grows because the quantum complexity of the state increases over time. The interior is not a fixed container. It is a growing space, generated by the ongoing computation of the quantum system. The singularity is the point where the computation outgrows the geometric container. What lies beyond the event horizon is a computation of ever-increasing depth and complexity. The Penrose process and the ergosphere of rotating black holes reveal that what lies beyond the event horizon is part of a dynamic thermodynamic system. Energy can be extracted from the ergosphere. The 4 laws of black hole mechanics mirror the 4 laws of thermodynamics. Black holes have genuine temperature and genuine entropy. Any description of the interior must be consistent with these thermodynamic properties. The exterior has finite temperature, finite entropy, and finite energy. The interior must be compatible. The gravitational path integral, which sums over all possible spacetime geometries, provides a powerful framework. Recent work showed that including replica wormholes in the sum reproduces the Page curve and preserves unitarity. The singularity, present in individual classical geometries, may be averaged away in the quantum sum. The full quantum theory may be singularity-free even though individual classical solutions contain singularities. This is analogous to quantum tunneling, where individual classical paths are blocked but the quantum sum over all paths allows passage. The Planck star hypothesis offers a concrete picture. What lies at the very center, replacing the singularity, is a tiny grain of matter at the Planck density, the densest possible configuration. The Planck star preserves information, has finite density, and eventually decays through a quantum transition. The black hole is temporary. The Planck star is the seed from which a white hole will eventually grow, releasing everything that fell in. The observational constraints from LIGO, the Event Horizon Telescope, and future detectors are tightening. Each merger tests general relativity. Each image constrains the near-horizon geometry. Future detectors may detect echoes, anomalies, or deviations that signal new physics. The gap between theory and observation is narrowing. The deeper truth about what lies beyond the event horizon is that the question itself may be poorly posed. The event horizon is a classical concept defined within the framework of general relativity. The interior is a classical concept. The singularity is a classical concept. But reality, at the most fundamental level, may not be classical. It may be quantum. And in the quantum picture, the sharp distinction between inside and outside, between horizon and interior, between the known and the unknown, may dissolve. The most profound insight from the study of black holes over the past 3 decades is that space-time is likely not fundamental. It is emergent. It arises from something deeper, something quantum mechanical, something informational. The evidence comes from multiple independent sources. The Bekenstein-Hawking entropy scales with area, not volume, suggesting the 3-dimensional interior is derived from 2-dimensional boundary physics. Mark van Ramsdonk showed that removing entanglement causes spacetime to disconnect. Daniel Harlow and colleagues showed that holographic spacetime has the structure of a quantum error-correcting code. Leonard Susskind showed that the interior volume grows with computational complexity. If spacetime is emergent, then what lies beyond the event horizon is not a region of fundamental spacetime. It is a region of emergent spacetime, a holographic projection generated by quantum information on the boundary. And at the center, where the classical theory predicts a singularity, the emergent description breaks down, the projection loses coherence, the hologram dissolves. What remains is not the classical singularity but the underlying quantum reality, the quantum information that generates the holographic projection, continuing to evolve smoothly and unitarily even when the projection itself fails. Let that sink in. The interior of a black hole may be real in the way that temperature is real. Temperature is an emergent property of molecular motion. It is genuine and measurable, but it does not exist at the level of individual molecules. Similarly, the interior of a black hole may be an emergent property of quantum information dynamics. It is experienced by a falling observer, but it does not exist at the most fundamental level. It is a projection generated by the quantum computation that constitutes the black hole. This perspective transforms the question of what lies beyond the event horizon. The question assumes that the interior is a region of space that you travel through. But if space is emergent, and if the interior is a holographic projection, then traveling through it is traveling through a projection. The journey from the horizon to the center is real at the emergent level, just as the temperature of a gas is real at the macroscopic level. But it may have no counterpart at the fundamental level, just as temperature has no counterpart at the level of a single molecule. The connection between entanglement and geometry provides the most profound perspective on what lies beyond the event horizon. Mark van Ramsdonk showed in 2010 that removing entanglement causes spacetime to disconnect. No entanglement, no spacetime. Space is held together by quantum correlations. The event horizon is where the pattern of correlations changes dramatically, where the entanglement between interior and exterior reaches its maximum and the geometry takes its most extreme form. Inside the event horizon, the entanglement structure that generates the emergent geometry becomes increasingly disrupted. The quantum state becomes more scrambled, more complex, more tangled. The geometric description, the emergent space-time picture, becomes less reliable. Near the center, the scrambling has reached its maximum. The complexity has exceeded the capacity of any geometric representation. The projection has lost coherence. What remains is pure quantum information, evolving unitarily, preserving information, but no longer expressible in the language of geometry. The error-correcting structure of holographic spacetime degrades near the center. The bulk geometry is encoded in the boundary through a quantum error-correcting code. Away from the center, the code is robust, the geometry is reliable, the emergent description works well. Near the center, the code has degraded, errors accumulate, the encoding becomes unreliable, the geometric description becomes meaningless. What lies beyond the event horizon, at the deepest level, is a region where the error-correcting code fails and the underlying quantum information demands a different kind of description. Susskind's complexity growth proposal adds dynamical content. The interior volume grows over time, even after thermal equilibrium, because the quantum complexity of the state continues to increase. The interior is not static. It deepens, stretches, expands. The singularity is the limit of this growth, the point where complexity exceeds geometric capacity. The interior is a growing space, generated by computation. The arrow of time points toward black holes. They are the maximum entropy objects. The total black hole entropy dominates the entropy of the cosmos. Roger Penrose has argued that the low entropy of the early universe is connected to gravity, and that the thermodynamic arrow ultimately leads to black holes. What lies beyond the event horizon is the thermodynamic endpoint, the destination of the arrow of time. But the information is not destroyed. The page curve is followed. Unitarity holds. The information is scrambled and encrypted, but preserved. What lies beyond the event horizon is not a place where information dies. It is a place where information is transformed, processed at the maximum rate, distributed across the boundary, and eventually returned to the outside through the Hawking radiation over timescales that dwarf the current estimated age of the universe. The scrambling time of a black hole provides a concrete measure of how the interior processes information. For Sagittarius A*, the scrambling time is on the order of milliseconds. Within thousandths of a second, information that crosses the horizon is distributed across the entire boundary, entangled with every other piece of information in the system. Patrick Hayden and John Preskill showed in 2007 that black holes saturate the fundamental quantum bound on scrambling speed. No physical system can process information faster. What lies beyond the event horizon is the fastest information processor in nature. The connection to the arrow of time deepens the picture. Black holes are the maximum entropy objects for a given mass. The total entropy of all black holes in the observable universe is estimated at roughly 10 to the power of 104, dwarfing the entropy of all non-black hole matter. The thermodynamic arrow of time points toward black holes. What lies beyond the event horizon is the end point of entropy maximization, the final state of the thermodynamic journey, the place where order has been maximally converted to disorder. But the information is not destroyed. The island formula confirms the page curve. Unitarity is preserved. The information that falls in is scrambled, encrypted, distributed, but not lost. What lies beyond the event horizon is not a place where information goes to die. It is a place where information is transformed, processed, and eventually returned to the outside universe through the Hawking radiation. The Bekenstein-Hawking entropy formula provides a powerful constraint on what lies beyond the horizon. The entropy of a solar mass black hole is roughly 10 to the power of 77. This means the interior has 10 to the power of 77 microscopic degrees of freedom. Whatever lies beyond the horizon must have enough internal structure to support this vast number of configurations. A true singularity, a point of zero volume, cannot accommodate any microstates. The entropy demands structure. The singularity denies it. Something must give, and what gives is the singularity. The Planck star concept, proposed within the loop quantum gravity framework by Carlo Rovelli and Francesca Vidotto, offers a concrete picture. What lies beyond the event horizon, at the very center, is not a singularity but a Planck star, a tiny grain of matter at the Planck density, the densest possible configuration. The singularity is replaced by the smallest, densest, most information-packed object that the laws of physics permit. The Planck star preserves information. It has finite density. And it eventually decays, converting the black hole into a white hole from which the information re-emerges. This is not science fiction. The Bekenstein bound sets a maximum on the information content of any region. Black holes saturate this bound. They are the densest information stores in nature. The interior processes this information at the maximum rate allowed by quantum mechanics, as shown by the Hayden-Preskill scrambling result. What lies beyond the event horizon is a maximum rate, maximum density quantum information system, the most extreme computational system that the laws of physics permit. The interior processes information at the fastest rate allowed by quantum mechanics, as demonstrated by the Hayden-Preskill scrambling result. It stores information at the maximum density allowed by the Bekenstein bound. It transforms structured information into scrambled information, with an efficiency that no other system can match. What lies beyond the event horizon is nature's ultimate computer, operating at the absolute physical limits of information processing, storage, and transformation. These are rigorous theoretical proposals, developed within well-defined mathematical frameworks, constrained by the most fundamental principles of physics. They do not tell us with certainty what lies beyond the event horizon, but they tell us what the answer must be consistent with. And the constraints are so tight, so demanding, so specific, that the range of possible answers is narrowing with every passing year. The concept of black hole complementarity, proposed by Susskind, Thorlacius, and Uglum in 1993, provides a framework for understanding the relationship between the interior and exterior descriptions. According to complementarity, the outside observer and the falling observer have different but equally valid descriptions of what lies beyond the event horizon. The outside observer sees information encoded on the horizon and eventually returned in Hawking radiation. The falling observer sees a smooth interior and a journey to the center. Both are correct. Neither is complete. No single observer can verify both descriptions simultaneously, because the event horizon prevents communication from inside to outside. If complementarity is correct, then the answer to what lies beyond the event horizon is observer-dependent. For the falling observer, the interior is whatever quantum gravity predicts: a bounce, a fuzzball surface, a breakdown of emergent geometry. For the outside observer, there is no interior. All the physics is on the boundary. The interior is a complementary description, not an independently real region of space-time. This is one of the most radical implications of the black hole physics program. Reality itself may be observer-dependent at the event horizon. The Planck star concept, developed within loop quantum gravity, offers one of the most concrete pictures of what might replace the singularity at the center. The Planck star is a compact object at the Planck density, the densest possible configuration of matter, with a radius of roughly the Planck length. It preserves information. It has finite density. And it eventually decays through a quantum transition that converts the black hole into a white hole. The matter that collapsed billions of years ago rebounds and re-emerges. The black hole is temporary. What lies beyond the event horizon is not a permanent prison but a very long-lived transition state. The connection between entanglement and geometry, established through the work of Van Ramsdonk, Harlow, Pestowski, Yoshida, Preskill, and others, provides the most profound perspective on what lies beyond the event horizon. If spacetime is woven from entanglement, then the interior of a black hole is a region where the entanglement structure has become extreme, scrambled to the maximum degree, processed at the fastest rate. The singularity is the point where the entanglement structure has exceeded the capacity of any geometric representation. What lies beyond the event horizon is a quantum system operating at the limits of nature, processing information at the maximum rate, storing information at the maximum density, scrambling information at the maximum speed. The error-correcting code that generates the holographic spacetime degrades near the center. The bulk geometry becomes unreliable. The projection loses coherence. What remains is the boundary theory, evolving smoothly and unitarily, preserving all information, but no longer generating a stable geometric image in the interior. The singularity is not a physical catastrophe. It is a representational failure. The underlying reality continues. The projection does not. This perspective is deeply strange. It says that what lies beyond the event horizon is not a region of three-dimensional space in the fundamental sense. It is a quantum computation whose output includes, among other things, the experience of three-dimensional space. When the computation reaches sufficient complexity, near the center, the spatial output becomes unreliable. The computation continues. The spatial representation does not. What lies beyond the event horizon, at the deepest level, is not a region of space. It is a quantum computation, running at the physical limits of information processing, generating the experience of space as one of its outputs, and failing to generate that output near the center where the computation has grown too complex for the spatial projection to sustain. The deeper truth is that what lies beyond the event horizon is a question about the nature of reality itself. The deeper truth about what lies beyond the event horizon connects to the most fundamental question in physics: what is reality made of? If spacetime is emergent, as the holographic principle suggests, then the interior of a black hole is an emergent region, a projection generated by quantum information on the boundary. The projection works well near the horizon, where the curvature is moderate and the error-correcting code is robust. It fails near the center, where the curvature is extreme and the code has degraded. What lies beyond the event horizon is a region where the emergent description progressively breaks down, revealing the deeper quantum informational substrate. The Bekenstein bound sets a maximum on the information content of any region of space. Black holes saturate this bound. They contain the maximum possible information for their size and energy. The interior is the most information-dense region in the universe. What lies beyond the event horizon is a maximum density information store, a system operating at the physical limits of information storage, processing that information at the maximum rate allowed by quantum mechanics. The connection between the interior and the arrow of time is important. Black holes are the objects of maximum entropy for a given mass. The total entropy of all black holes dominates the entropy of the cosmos. The thermodynamic arrow of time points toward black holes. What lies beyond the event horizon is the thermodynamic endpoint, the place where entropy has been maximized, where order has been fully converted to disorder, where the arrow of time has reached its target. But the information is not destroyed. The page curve is followed. Unitarity is preserved. The information is scrambled and encrypted, but not lost. What lies beyond the event horizon is a quantum system that transforms structured information into scrambled information at the maximum possible rate, preserving every bit while making it maximally difficult to decode. The complementarity principle adds the final layer. What lies beyond the event horizon may depend on who is asking. For the falling observer, the interior is a real space-time region, experienced and traversable. For the outside observer, the interior is a redundant description, a complementary encoding of physics that is fully captured on the boundary. Both descriptions are valid, neither is complete. The full picture requires a framework that encompasses both, a framework that we call quantum gravity, and that we do not yet possess. It is a question about whether spacetime is fundamental or emergent, whether information is more basic than geometry, whether the three-dimensional world we experience is the deepest layer or a projection. The event horizon is not just the boundary of a black hole. It is the boundary between the emergent and the fundamental, between the classical and the quantum, between the described and the indescribable. And crossing it, even in theory, is crossing from one level of reality to another. The journey from the event horizon to the center is a journey from the emergent to the fundamental, from the geometric to the informational, from the classical to the quantum. Each step deeper takes you further from the familiar world of space-time and closer to the quantum substrate from which that world emerges. What does it mean that the universe contains boundaries behind which our understanding completely changes? What does it mean that the event horizon separates the known from the unknown, the classical from the quantum, the emergent from the fundamental? It means that we live in a universe with layers. The surface layer, the layer of space-time and classical geometry, works extraordinarily well at everyday scales. It describes the bending of light, the orbits of planets, the expansion of the universe, the propagation of gravitational waves. This layer has been tested with extraordinary precision. It has never failed at the scales where it has been tested. But the event horizon tells us that the surface layer is not the bottom. Beneath it lies something else, something quantum, something informational, something that we can glimpse only at the extremes, only at the Planck scale, only beyond the event horizon where the classical description fails. The event horizon is the window through which the deeper layer is visible, and what we see through that window has already changed everything. There is a philosophical pause required here. The event horizon confronts us with the limits of knowledge. We cannot observe the interior directly. We cannot send instruments behind it and receive their data. We can only infer, from theory and from consistency arguments, what lies beyond. This is an unusual position for physics, a discipline that prides itself on experimental verification. At the event horizon, we are forced to rely on theoretical reasoning alone, constrained by the twin pillars of general relativity and quantum mechanics, guided by consistency and mathematical beauty, but without the anchor of direct observation. And yet the theoretical reasoning has been remarkably productive. The information paradox, the firewall, the holographic principle, the island formula, ER equals EPR, the connection between entanglement and geometry, quantum error correction, computational complexity, all of these were discovered or sharpened by the attempt to understand what lies beyond the event horizon. The question has driven some of the most important advances in theoretical physics of the past half-century. The study of what lies beyond the event horizon has driven the most important theoretical advances of the past half-century. The information paradox launched the entire field of quantum gravity phenomenology. The holographic principle transformed our understanding of the relationship between gravity and quantum mechanics. The ADS-CFT correspondence became the most powerful computational framework in theoretical physics. Quantum error correction connected the physics of black holes to the technology of quantum computing. Gravitational wave astronomy opened an entirely new observational window. The practical applications are substantial. Quantum error correction inspired by holographic spacetime, is essential for building fault-tolerant quantum computers. The mathematical tools from ADS, CFT have applications in condensed matter physics, nuclear physics, fluid dynamics, and materials science. The thermodynamics of black holes has illuminated the physics of strongly coupled quantum systems. The philosophical implications are profound. The event horizon forces us to confront the limits of observational knowledge. We cannot see beyond the horizon. We must rely on theory alone. This is an unusual position for physics, but the theoretical reasoning has been remarkably productive, generating insights that have transformed multiple fields. The next generation of observations will constrain the theories further. Future gravitational wave detectors, both ground-based and space-based, will provide more precise measurements. The Event Horizon Telescope will sharpen its images. Each observation will narrow the range of possible answers. The convergence of theory and observation is real and measurable. What lies beyond the event horizon also confronts us with the nature of existence. If spacetime is emergent, if the three-dimensional world is a projection, if information is more fundamental than geometry, then the question of what lies beyond the horizon is not just a question about a particular astrophysical object. It is a question about what reality is at the deepest level. The answer will not merely describe the interior of a black hole, it will describe the substrate of existence itself. We are beings who evolved on a small planet under moderate conditions, and yet we have developed the intellectual tools to ask what lies behind the most impenetrable boundary in the cosmos. We have detected the gravitational waves from merging black holes a billion light-years away. We have photographed the shadow of a black hole across 55 million light-years. We have developed mathematical frameworks that describe quantum information dynamics at scales far beyond any direct experimental access. The fact that we can ask this question and get this close to an answer is itself remarkable. The philosophical dimension of this question deserves attention. The event horizon forces us to confront the limits of observational knowledge. We cannot see beyond it. We must rely on theory. And the theory is not yet complete. We are in the unusual position of knowing that something profoundly important lies beyond the horizon, knowing that our current theories are inadequate to describe it fully, and knowing that the resolution will require ideas we do not yet have. This is both humbling and inspiring. Humbling because it reveals the incompleteness of our understanding. Inspiring because it shows us exactly where to look for the next breakthrough. The practical applications of this research continue to expand. Quantum error correction for quantum computing, holographic methods for strongly coupled physics, gravitational wave astronomy for testing general relativity. Each application strengthens the connection between the most abstract questions and the most practical technologies. The question of what lies beyond the event horizon, the most abstract question in physics, has generated tools that are building quantum computers, advancing materials science, and transforming our understanding of strongly interacting quantum systems. The darkness beyond the horizon has illuminated corners of science that seem to have nothing to do with black holes. This is one of the remarkable features of fundamental physics. The deepest questions generate the widest applications. The practical implications extend beyond abstract theory. Quantum error correction, inspired by the holographic structure of spacetime, is essential for building fault-tolerant quantum computers. The ADS CFT correspondence has been applied to problems in condensed matter physics, nuclear physics, and fluid dynamics. The thermodynamics of black holes has illuminated the physics of strongly coupled quantum systems. Gravitational wave astronomy has opened an entirely new observational window onto the universe. The observational landscape is evolving rapidly. Future gravitational wave detectors, both ground-based and space-based, will detect more mergers with greater sensitivity. The Event Horizon Telescope continues to improve. Future observations may resolve the photon ring, a sharp, bright feature near the horizon that encodes geometric information about the spacetime geometry. If quantum gravitational effects modify the near-horizon geometry even slightly, these observations might provide the first indirect evidence about what lies beyond. The next generation of physicists will have tools we can barely imagine, quantum computers powerful enough to simulate aspects of quantum gravity, gravitational wave detectors sensitive enough to detect near-horizon quantum effects, theoretical frameworks more refined and more constrained than anything available today. The resolution of the question, what lies beyond the event horizon, may come not from a single breakthrough, but from the gradual convergence of observation, computation, and theory over decades. What lies beyond the event horizon also matters for our understanding of ourselves. We are beings who evolved on a planet, under moderate conditions, with brains adapted for the challenges of survival. And yet we have developed the intellectual tools to ask what lies behind the most impenetrable boundary in the cosmos. We have built detectors that measure the stretching of spacetime by less than 1,000th of the diameter of a proton. We have built telescopes that image the shadow of a black hole across 55 million light-years. We have developed mathematical frameworks that describe the quantum information dynamics of systems so extreme that no experiment can probe them directly. The fact that we can ask this question, the fact that we can get this close to an answer, is itself a testament to the power of human curiosity and the reach of mathematical reasoning. The event horizon is not just the boundary of a black hole, it is the boundary of our knowledge, and what lies beyond it, when we finally understand it, will reveal the deepest truth about the nature of reality. Not because the interior of a black hole is special, but because the interior of a black hole is where our theories are tested most severely, where the deepest assumptions are challenged most directly, and where the next great revolution in physics must begin. The question of what lies beyond the event horizon has driven advances across physics, from fundamental theory to practical technology. The singularity problem inspired string theory and loop quantum gravity. The information paradox inspired holographic duality and quantum error correction. Hawking radiation inspired the study of quantum fields in curved spacetime. The firewall paradox inspired the ER equals EPR conjecture and the island formula. Gravitational wave astronomy was motivated in part by the desire to test general relativity in the strong field regime near event horizons. The mathematical tools developed for this question have found applications in condensed matter physics, nuclear physics, fluid dynamics, quantum computing, and cryptography. The holographic correspondence has been used to compute transport coefficients in strongly coupled plasmas, providing predictions that agree with experiments at heavy ion colliders. Quantum error correction, inspired by the holographic encoding of spacetime, is the foundation of fault-tolerant quantum computing. The study of the event horizon has revealed connections between physics and mathematics that no one anticipated. Penrose introduced topological methods to general relativity. The holographic principle connected gravity to information theory. ADS, CFT connected gravity to quantum field theory. Error correction connected gravity to quantum computing. Each connection was discovered through the study of the event horizon and its interior. The event horizon has been the most productive catalyst for interdisciplinary collaboration in the history of physics. The observational frontier is advancing rapidly. LIGO and Virgo have detected roughly 90 gravitational wave events. The Einstein Telescope and Cosmic Explorer, next-generation ground-based detectors, will increase sensitivity by an order of magnitude. LISA, the space-based detector planned for the coming decades, will detect supermassive black hole mergers. The Event Horizon Telescope is being upgraded with new stations and frequencies. Each new instrument, each new observation, tightens the constraints on what lies beyond the event horizon. The study of what lies beyond the event horizon has also revealed unexpected connections between physics and mathematics. Penrose's singularity theorem introduced topological methods to general relativity. The holographic principle connected gravity to information theory. ADS, CFT, connected gravity to quantum field theory. Error correction connected gravity to quantum computing theory. Each connection was unexpected and was driven by the attempt to understand the event horizon and its interior. The practical applications are growing. Quantum error correction is essential for fault-tolerant quantum computers. The ADS CFT toolkit has applications in materials, science, and nuclear physics. The thermodynamics of black holes illuminate strongly coupled quantum systems. The singularity problem, the most abstract question in physics, has generated practical tools with real-world impact. The philosophical dimension is equally important. The event horizon forces us to confront the limits of observational knowledge. Can physics proceed without direct experimental verification? Can mathematical consistency alone guide us to the truth? The history of the event horizon problem suggests that it can. The theoretical insights generated by this question have been confirmed, at least indirectly, by every observation that has ever been made. The consistency constraints are powerful. The convergence is real. The answer is emerging, even without direct observation of the interior. What lies beyond the event horizon? The honest answer is that we do not know. Not yet. Not with certainty. But we know more than we did a decade ago, and we will know more a decade from now. The answer is emerging, slowly, from the convergence of independent theoretical approaches, from the tightening of observational constraints, from the patient accumulation of insight by thousands of physicists working across generations. General relativity says the interior is a collapsing spacetime, with space and time inverted, with a singularity in the future that cannot be avoided. Quantum mechanics says the singularity cannot exist, that information must be preserved, that the interior must be consistent with unitarity and the holographic bound. String theory says the interior might be a fuzzball, a complicated web of stringy material with no singularity and no smooth horizon. Loop quantum gravity says it might be a quantum bounce, connecting a black hole to a white hole through a Planck scale transition. The holographic principle says it might be a projection, a three-dimensional image generated by two-dimensional boundary physics. The firewall proposal says the smooth interior might not exist at all. ER equals EPR says it might be threaded with wormholes. Complementarity says it depends on who is asking. Each of these proposals captures a piece of the truth. None captures all of it. The final answer, the theory that tells us definitively what lies beyond the event horizon, will be the theory of quantum gravity. It will unify general relativity and quantum mechanics into a single consistent framework. It will resolve the singularity. It will preserve information. It will reproduce the Bekenstein-Hawking entropy. And it will, for the first time, give us a reliable picture of the region beyond the boundary from which nothing returns. The event horizon is the most absolute boundary in nature. Nothing crosses it outward. No light, no matter, no information, no signal of any kind. And yet this boundary, this impassable wall, has taught us more about the nature of reality than perhaps any other object in the cosmos. It has revealed that space-time may not be fundamental. That information may be more basic than geometry. That entanglement and wormholes may be the same thing. That the three-dimensional world may be a holographic projection. Every great revolution in physics has been triggered by a boundary between the known and the unknown. The boundary between classical and relativistic mechanics at the speed of light led to special relativity. The boundary between classical and quantum behavior at the atomic scale led to quantum mechanics. The boundary between Newtonian and Einsteinian gravity at extreme curvatures led to general relativity. The event horizon is the latest and deepest such boundary, and the revolution it demands will be the most profound yet. The resolution will come. It may come from string theory or loop quantum gravity, or holographic duality, or computational complexity, or some approach not yet imagined. It may come from a single brilliant insight, or from the gradual convergence of many partial results over decades, but it will come. Human curiosity does not accept permanent barriers. It does not accept the phrase "we cannot know." It pushes forward, always, into the darkness. What lies beyond the event horizon is more than a physics question. It is a human question. A question about what we are capable of understanding, what we are willing to attempt, what we refuse to accept as unknowable. The event horizon says nothing escapes. Human curiosity says, "Watch me." What lies beyond the event horizon is the central question of 21st century physics. It connects gravity to quantum mechanics, information to geometry, entropy to time, computation to existence. The answer will not merely describe the interior of a black hole, it will describe the fabric of reality at the deepest level. The event horizon has been patient. It has been there since the first black hole formed. It has watched while we developed general relativity, quantum mechanics, string theory, holographic duality, gravitational wave astronomy. It has waited while we argued about firewalls and fuzzballs and islands and wormholes. And it will continue to wait, silent and absolute, until the theory of quantum gravity is finally written and the deepest secret of the cosmos is revealed. The answer is coming, not today, perhaps not for decades, but the convergence of theory and observation is real. The constraints are tightening, the possibilities are narrowing. The outlines of the answer are emerging from the darkness, and when the answer finally comes, it will change everything. What lies beyond the event horizon is the truth about what the universe is, and we are closer to that truth than we have ever been. Closer because of every gravitational wave detection. Closer because of every event horizon telescope image. Closer because of every theoretical advance. Closer because of every mathematical insight. The truth is there, behind the horizon, waiting to be understood, and we will understand it, because that is what we do. Because that is what it means to be human in a universe full of darkness and mystery and unanswered questions. The history of physics is a history of boundaries crossed. The boundary between terrestrial and celestial mechanics was crossed by Newton. The boundary between mechanics and electromagnetism was crossed by Maxwell. The boundary between classical and quantum was crossed by Planck and Bohr and Heisenberg. The boundary between Newtonian and relativistic gravity was crossed by Einstein. Each crossing revealed a deeper layer of reality. The event horizon is the next boundary, and the crossing, when it comes, will reveal the deepest layer yet. The resolution may require accepting that space and time are not fundamental, that the three-dimensional world is a holographic projection. That information is more basic than geometry. That the universe is, at its deepest level, a quantum computation whose output is the reality we experience. These ideas, once speculative, are now supported by rigorous mathematical results within the ADS CFT framework, by the connection between entanglement and geometry, by the error-correcting structure of holographic spacetime, by the scrambling and complexity dynamics of black holes. What lies beyond the event horizon is the answer to the deepest questions physics has ever posed. What is spacetime made of? What is information? What is reality? The event horizon is not just the boundary of a black hole, it is the boundary of understanding. And the quest to cross it, intellectually if not physically, is the greatest adventure in the history of human thought. The answers we seek are not just about black holes, they are about the nature of existence. They are about what spacetime is made of, what information is, what consciousness is, what it means for something to be real. The event horizon contains, locked behind its impenetrable boundary, the answers to the most fundamental questions that any civilization can ask. What lies beyond the event horizon? Perhaps a collapsing spacetime heading toward a quantum bounce, perhaps a fuzzball of strings, perhaps a holographic image that dissolves at the center, perhaps a computation of ever-growing complexity, perhaps all of these, depending on which level of description you use. The event horizon is where the levels of description diverge, where the classical and the quantum part ways, where the emergent and the fundamental reveal themselves as different stories about the same underlying reality. The boundary between known and unknown has been the engine of physics since Newton first asked why things fall. The event horizon is the latest and deepest such boundary. And what lies beyond it, when we finally understand, will not merely answer a question about black holes. It will answer the question about what the universe is made of at the deepest level, what space-time is, what information is, what existence is. Somewhere, right now, the answer is taking shape. In an equation being written, in a calculation being run, in a thought being thought. The event horizon is patient. It has waited since the first black hole formed. It will wait until the theory is ready, And when the theory comes, the boundary will finally yield its secret, and everything we thought we knew about the universe will change. What lies beyond the event horizon is the answer to everything, and we are closer to it than we have ever been. The event horizon is the most absolute boundary in nature and the most productive source of new ideas in physics. The questions it poses about information, entropy, unitarity, emergence, and the nature of spacetime are the deepest questions science has ever asked, and the answers, when they come, will change not just our understanding of black holes but our understanding of everything. The horizon waits. It has waited since the first black hole formed. It will wait until the theory of quantum gravity is written, silent, absolute, patient beyond measure. And we keep looking, keep calculating, keep reaching toward the darkness, because the darkness is where the truth is hiding, and the truth, whatever it turns out to be, will be worth the journey. Because the truth is not just about black holes, it is about what the universe is made of at the deepest level. It is about whether space and time are fundamental or emergent. It is about whether information is the most basic substance in nature. It is about what it means to exist. These are the questions that the event horizon poses, silent and absolute, from the center of every galaxy in the cosmos. The horizon waits. It has waited through every observation we have made, every equation we have written, every debate we have conducted, and so do we. Reaching toward the answer with every mathematical tool and every physical instrument at our disposal, the journey is not over. It may not be close to over, but the direction is clear. And the destination, the understanding of what lies beyond the event horizon, is worth every step of the long road ahead. The horizon waits, and so do we.